So we want to learn how to balance permanganate half cell reaction. All we'll be doing here is learning how to balance the half cell reaction of permanganate titration. Now we have permanganate ion and we have manganese 2 plus. Now from what we've explained, we know that the oxidation state of manganese in permanganate ion here is +7, and here manganese ion is depicted here. They showed us that it is +2. Okay, so this is +2. Now I've told you, so this indicates that it has accepted electron and it is reduced. Now how many electrons did it accept? So you have to differentiate, you have to minus it. That's 7 minus 2. 7 takes away 2, 5. So it's indicated, it shows that manganate and permanganate ion accepted 5 electrons in the reaction process to become reduced to 2. So we'll say MnO4 minus plus 5 electron, accepted 5 electron to become Mn2 plus. This is balanced in a way in terms of permanganate, because from +7 it reacts to change to +2, shows that it's accepted 5 electrons to get to +2. But we have oxygen here, we don't have oxygen here. This is kind of showing us that the equation is not truly balanced, because if the equation is balanced, we need to have oxygen at both sides of the reaction. Now since we have 4 oxygen here, it indicates that we have to put water in the reaction side, water molecule in the reaction side. That's Mn2 plus because the oxygen is 4, so it has to be 4 molecules of water. 4 oxygen, it has to be 4 molecules of water. So that's 4 oxygen. Now since there's 4 molecules of water, that's 4 oxygen and 8 hydrogen. There are 8 hydrogen, and there's no hydrogen here. It indicates that in the reaction part we have to put 8 hydrogen. 8 hydrogen has to be in the reaction, in the reactant part. Since we've balanced oxygen as 4, but there's no hydrogen in this, there's no hydrogen in the reaction part, there's no hydrogen in the reactant part. So we indicated here as water, 4 times 2, 8, 4 oxygen, that's balanced, but there's no hydrogen, so we have to put 8 hydrogen here, and it becomes MnO4 minus plus 5E minus plus 8 hydrogen. Now this is partly balanced too, so we have to know if, definitely we have to put a positive charge here. But do you know why we put a positive charge? This positive charge is to sum up both the reactant parts, the ions in the reactant parts and the ions in the product parts. Now if you look at the ions in the reactant part, this is given in this part, we have 8 positive ion, 8 plus, minus 1. This is 1 minus 1. I know this is plus 5, it indicates it's lost. That's minus 5. If this plus 5 electron means it accepts electron, that it looks like it's lost, as I explained, plus 7 minus 5 plus 2. So it's indicating minus 5. So we have plus 5 meaning minus 5. If you minus each of all these things, we have 8 minus 1. That's it's 8 minus 1 is what? 7. And 7 minus 2 is what? 7 minus 5 is 2. So we have plus 2, a total of plus 2. So 8 minus 1, 7. 7 minus 2, 5. So the total electrons in the reactant part is plus 2. What about the product part? Does it match? So we have here nothing, there's no ion here, that's 0. And we have 2 here, that's 2 plus 0 is equals to plus 2, indicating that both the reactant part and both the product part is balanced. So telling us that this reaction is a balanced one. We've balanced it half cell in the half cell notation. This I should be in the half cell notation. But there's something I would like to point out. It's saying that 1 mole, of Kn NO4 required 5 electrons. It accepted 5 electrons. So to get, I remember in when we were talking about acid-base titration, I told you that we'll also talk about equivalent points of reducing and oxidizing agents. Now, it indicated that the equivalent weight of KMnO4 would be equal to the mass of KMnO4 divided by 5, because it lost 5 electrons. I'm sorry, it's accepted 5 electrons from this. So generally, it is said that the equivalent weight of an oxidizing or reducing agent will be equal to the mass of the oxidizing, let me put it, of the oxidizing or reducing agent divided by the electron lost or gained. So this will be the formula to get the equivalent weight of an oxidizing or reducing agent. You get the mass of the oxidizing agent, and you're dividing it if the amount of electron is lost, if it's a reducing agent, divided by the amount of electron it gained with an oxidizing agent. So this is the total half cell equation of permanganate reaction. This is the complete half cell reaction of permanganate reaction. Then this is the equivalent weight, the formula for the equivalent weight of KMnO4. The equivalent is the mass of the KMnO4 divided by 5. This 5 is gotten from the amount, the 5 electron it's lost. It accepted 5 electron. That's how we got this 5. So we derive the formula for equivalent weight of an oxidizing agent or a reducing agent as the mass of the oxidizing or the reducing agent divided by the electron lost or gain. Now we'll talk about the application of permanganate titration in the estimation of ferrous salt. Now here, ferrous 2 is the reducing agent because it is oxidized. We know ferrous 2 is the reducing agent because it's oxidized to ferrous 3, while KMnO4 is the oxidizing agent because it is reduced. It is reduced to Mn2 plus from +7 to Mn2 plus, while ferrous is oxidized to Fa3 plus. KMnO4 is reduced to Mn2 plus from +7. So you see that this is an example of a perfect redox titration because it involves a reducing agent and an oxidizing agent. Now we'll try to balance the equation of ferrous titration involving permanganate titration. Now we'll have to get our half cell equation of permanganate titration. We've already derived it as this. So we'll bring it forward as saying NO4 minus plus 5 electron plus 8 plus to give Mn2 plus 4H2O. That's for the half cell of permanganate. Now let's get the half cell of ferrous rather. So ferrous 2 plus goes to give Fe3 plus E minus. Now we have to check, is this balanced? Yes, this is balanced because we have one ferrium, we have the reactant side, the oxidation number of the total reactant side, we have +2, and the product side, the oxidation number, remember I told you this, once you see an electron means minus, means is +3 minus 1, that's what, +2. So this reaction is balanced. So this is the half cell reaction for ferrous titration. This reaction is balanced. 1 1. We have 1 mole, 1 mole, 1 mole of ferrium, 1 mole of ferrium. Then in terms of oxidation state, this is +2 in the reactant side. In the product side, that's 3 minus 1, that's +2. So the balanced one. So we have to join this together. We'll then join this together. And when we are trying to impute this to this, we are going to cross multiply. I'll put it cross multiply both sides with their electron. You know, here we have the amount of electron lost here as 5, and the amount of electron lost here as 1. That's 1 electron. Now we have to cross multiply to join these two equations together. we'll say that will be timesing this by 1 electron of ferrium, as the amount of electrons is lost. Then timesing this by 5. As I say, cross multiply. This times this whole reaction, this times this whole reaction, this times this whole reaction, and this will times this whole reaction. Then when we times it, we'll have this will still be the same, as since you are timesing one is timesing everything, because MnO4 minus plus 5E minus plus 8H plus to give Mn2 plus 4H2O. Then this, you are timesing it is 5. That's 5 will times everything in this bracket. That's 5E2 plus to give 5E3 plus 5E minus. Now because we have 5E, 5E, they cancel out. Then they cancel out. So we join the reactant side and the product side together. That's MnO4 minus reacting with plus 5E2 plus 8 hydrogen plus to give Mn2 plus reacting with the product side plus 5E3 plus 4H2O. So the final reaction is MnO4 minus plus 5E2 plus H plus to give Mn2 plus 5E3 plus 4H2O. So this is the final end product of the reaction.